Hello, everyone. My name is Jerry, and today we'll be presenting conditional entropy coding for efficient video compression. Efficiently storing videos is crucial to an enormous number of settings, from online media to self-driving cars, which store a massive quantity of data per day. This requires the use of good lossy video compression algorithms to reduce the bitrate of the massive quantity of data from videos, as well as reduce storage costs. Traditional video codecs such as H.264 and H.265 typically focus on explicit transformations to exploit the redundancy between video frames and reduce bitrate. Rather than encode every frame independently as an image, these codecs typically employ some form of motion warping, where the image in the previous frame is warped to the current with a flow field. The residuals between the source image and the warped image are then coded as well. This setup saves more bits than encoding every image independently. Recently, deep video compressors generalized this notion of explicit transformations across time using neural networks, where the current frame is still encoded as a function of the previous frame and the current residual. Many of these prior works can be quite slow, though, and hard to generalize to test data. In our work, we design a very simple video compression approach that only relies on an entropy model with no explicit transformations across time. Specifically, each frame is transformed to a code independently, and we only use the past frame to model the probability of the current code rather than affect its reconstruction through explicit transformations. This makes our approach very fast. We also propose an internal learning extension where we can directly optimize the video encodings during test time for an even better rate distortion trade-off. While this increases encoding time, decoding time is unaffected. So let's dive into this a little bit deeper at the encoding stage. In our entropy-only approach, each frame is independently transformed to a latent code using an image compressor. Let's assume the frame at t-1 is the first frame of the sequence. Using an entropy model, we model the prior probability of the latent code at t-1, or yt-1. The better we can model the likelihood of the latent code, the lower the entropy. And according to Shannon's source coding theorem, the lower the bit rate as well. These probabilities are directly fed into an entropy coder to produce the final compressed bit stream. Now for the current frame t and all subsequent frames, we can actually use yt-1 in the previous frame as input to produce a conditional entropy model, modeling the conditional probability of the current code yt given yt-1. The intuition here is that conditioning on the previous code will give us more certainty in predicting the current code probabilities than a simple prior model, reducing the entropy and bit rate even further. So let's describe the architecture of our conditional entropy model. Our entropy model relies on this additional code called a hyperprior code, in addition to the previous latent code yt-1 to help predict the probability of yt. This hyperprior code captures side information beyond the information provided by yt-1. For example, it can capture artifacts, motion, or changes in appearance. It's a similar idea to the residual frame used in previous approaches, but here we're using it as the entropy model. Let's denote this hyperprior code as ZT. Both yt-1 and yt are fed to a hyperprior encoder, producing this hyperprior code. This hyperprior code and yt-1 are fed through a hyperprior decoder to produce the probability distribution of the current code, yt. This hyperprior helps to reduce the entropy of the conditional probability distribution, but comes at the cost of having to be encoded itself. During decoding, the reverse process follows. We first decode the hyperprior bit stream at t-1 to recover the hyperprior code. We feed this hyperprior code into our entropy model to recover our prior probability distribution on the code bit stream in order to recover the image code yt-1. This latent code is then fed through an image decoder to obtain our reconstructed image at time t-1. Next, we consider frame t. we again first decode the hyperprior code at time t. Then, given the hyperprior code and the previous image code yt-1, we obtain the conditional probability distribution to recover our image code yt from the code bit stream. Similar to the previous frame, we can reconstruct the current frame through an image decoder as well. Our training loss optimizes for the classic rate distortion trade-off, where distortion is typically measured by L2 error of the reconstruction, and bit rate is approximated by the cross-entropy loss. After training the model, though, we asked the follow-up question: why can't we also optimize for this loss during test time? Does the model need to be fixed? It turns out you can optimize for the model for this loss during test time. For a given test video sequence, you can optimize the latent codes during encoding as much as you want, as long as the decoder is fixed. This is because a fixed decoder provides a consistent code book from which we can decode the bit stream back into symbols, but this provides no restriction on the encoding stage. So we hence optimize the codes with gradient descent during encoding. This trades off encoding runtime with better rate distortion performance, but we note that decoding runtime is unaffected. We evaluate our method on many datasets, from an internal self-driving dataset called North America to UVG, CDVL, and others, spanning a wide range of resolutions and frame rates. We benchmark against traditional video codecs such as H.265 and H.264 on the slowest settings in FFmpeg, as well as against prior work on deep video compressors. Our runtime plots below indicate runtime on the x-axis and MSIM on the y-axis for a roughly equivalent bitrate. We can see that our base model achieves competitive MSIM while being much faster than previous deep methods. Our internal learning extension does add encoding runtime costs due to gradient optimization during encoding time. However, it leaves decoding costs unaffected while improving MSIM from the base model by an additional 10%. On a standard plot displaying bitrate versus distortion, where higher curves are better, our approach, highlighted in purple, achieves competitive performance with video codecs and prior works on both North America and UVG. Our method especially excels compared to traditional video codecs during higher motion and lower frame rate settings. Here, we plot the rate distortion curves on the entire North America subset. And here we show the curve when only evaluated on moving vehicle sequences where the camera itself is moving. The gap between our approach and H.265 is much higher. Similarly, we plot the rate distortion curve on standard definition CDVL videos, and then we see that when the frame rate is lowered, our approach performs much better. Next, in this video sequence, we demonstrate qualitative video comparisons of our method versus H.265 on both UVG videos and North America. Here, we see that our reconstructed flag contains fewer artifacts than H.265 does. Next, in the jockey video sequence, we also demonstrate how our independent frame encoding produces less motion artifacts around the jockey. And finally, in an example North America self-driving video sequence, we demonstrate that our reconstructions create fewer artifacts on the car as compared to H.265. In summary, we presented a novel video compression method that is very simple and only models the conditional entropy between frames. We show that internal learning can be used to further optimize rate distortion without affecting decoding. Our approach is competitive with the state of the art while being faster. Thank you, and come check out our Q&A.